Thank you. First of all, I will express my gratitude to Mario Yurik, Eric Ford, and Pete Hatt for inviting me at this workshop. It is a pleasure for me to meet with you and the other participants to discuss about AstroGPU potentiality. I hope this is just the beginning of a relationship between us. Please feel free to call me at any time to discuss your needs. Today, I will talk about the CUNBODY ON library to accelerate particle-particle interaction for N-body simulation with GPU. In our laboratory, we are evaluating the GPU cluster in N-body simulation, such as cosmological N-body simulation and molecular dynamics simulation. The target code for our applications are P3M, particle mesh eval, and 3PM code. In the N-body simulation, the system is composed of a large amount of particles interacting with each other. For example, in the cluster system, in the star cluster system, we can regard stars as particles. In the cluster of galaxies, we can regard galaxies as particles. In protein or crystal, atoms are treated as particles. The most important part of computations is calculating the interaction between particles. The CUNBODY ON library is the first implementation of accelerating particle-particle interaction in gravitational N-body simulation using CUDA and NVIDIA GeForce 8800 GTX GPU. Figure shows the basic structure of our system. The system consists of a GPU and a host computer. The GPU calculates the interaction between particles. The host computer performs all other calculations. This idea is almost same as great system. Up to now, a lot of reports are published about N-body simulations with GPU. But a breakthrough exists at my report. What is the difference between past reports and my report? The key to breakthrough is a combination of GeForce 8800 GTX and CUDA. The GTX can run maximum 8192 threads in parallel. The peak speed reaches 345 gigaflops. Using traditional programming language such as CG, GPU threads cannot scatter information to any part of DRAM memory, even if we use GTX. But using CUDA language, we can use the scatter memory operation. And fortunately, by chance, my report is the first result of the GTX and CUDA for N-body simulation. We can achieve over sustained 300 gigaflops in very simple N-body simulation. We use GeForce 8800 GTX GPU and Quartz Duo or E4400 host computer, and also CUNBODY ON library. Then I show a demonstration. Sorry. First of all, I ran the simulation code without GPU. The initial condition is Plummer sphere of 8,192 particles. This is real-time calculation without GPU. So, n three-dimensional calculation, and n is the total number of particles, and this calculation speed is about 1.0 gigaflops by the quartz E6700. So next I will use the GPU. Note that this algorithm is not practical one. Shared time step and direct summation. Just a simple test. So next, 30,000 particles, about about 380 gigaflops. So with this CUNBODY 1 library, the total number of threads on GPU is 2048. The 2048 threads calculating force on different I particles. This approach for decomposition we call the particle decomposition or I parallelization. In the simple test, we find the CUNBODY 1 library and GForce display quite good performance. Secondly, we try to apply our library to the hierarchical tree algorithm. The tree algorithm is one of the first algorithms which reduces the calculation cost from order n square to order n log n. In this algorithm, the force from a distance node is replaced by the force from its center of mass. The histogram shows the number of I particles for each GPU cores and the ratio in the tree algorithm with 2 megaparticles. In the tree algorithm, neighboring particles are grouped and one interaction list is shared among the particles in the same group. Forces from particles in the same group is directly calculated on GPU. The tree algorithm reduces the calculation cost of the host computer by roughly a factor of ng, where ng is the average number of particles in a group. On the other hand, the amount of work on the GPU increases as we increase ng. Since the interaction list becomes longer, there is therefore an optimal ng at which the total computation time is minimum. The optimal ng strongly depends on the ratio of the speed of the host computer, GPU, and communication. We found ng around 500 gives the minimum computation time for GForce 8008 GTX. In this situation, the efficiency of GPU strongly depends on the NG and the particle decomposition number. If we use 2048 as particle decomposition number, almost all GPU will sleep, since the number of threads on GPU is 2048. So we prepare another version of CUNBODY 1 library for tree algorithm. The change we add to our library is the force decomposition. In the force decomposition, all GPU threads divided into 16 blocks, and each block calculates the same 128 I particles. After calculation, the force on 16 blocks are summarized on the host computer. Using force decomposition, we can reduce the particle decomposition number and increase the efficiency of GPU. Using the CUNBODY 1 library with the force decomposition, we measure the performance of tree algorithm. When we use the total number of 2 megaparticles, we need 2 hours to calculate for 100 time steps, 1,000 time steps. So the calculation speed achieved about 70 gigaflops. In the current library, the reduction of forces from all 60 blocks is done by host computer. So the bottleneck of the library is the communication between the host computer and GPU. If we can improve our library to do the reduction operation on GPU, the performance will become 140 gigaflops, maybe. Conclusion. We show the CUNBODY 1 library, the first implementation of accelerating particle-particle interaction in N-body simulation using GeForce 8800 GTX and CUDA. It performed over 300 gigaflops in direct summation algorithm and 70 gigaflops in hierarchical tree algorithm. In the tree algorithm, there is still room for the improvement of fast reduction scheme. Acknowledgement. I express acknowledgement to a lot of people for my AstroGPU research. 矢作、牧野、福重、河合、安田、藤川、高平、松原、恵比寿崎、中村、成美、中里。Thank you. Any questions?
Maybe one or two quick questions? Beck?
Right. For delusional stellar systems, we have to first treat the close binary stars, which vastly complicates the code. Has there been any effort to develop codes for GPUs, like say the RSET code or Kira, which handle that?
Talk about that. I think about the dense stellar cluster, Simon Tubart is expert. But the problem about the force reduction exists also in the dense stellar cluster simulation.
What
can you say about errors in force calculation and the number growth?
Yes, the rounding error increases the number of particles.
Okay, well, maybe we'll have Simon start setting up and thank our speaker again.